All right, so we're going to start sort of looking at statistics, and it's not going to sound like it in this particular note section, but it really does apply. So, for example, if you collect some data, that's what statistics is, right? You collect some data like test scores, and you plot those test scores in a coordinate plane. Those dots could make a particular shape, and we're going to want to model or come up with an equation for those for that shape of dots. Well, depending on the shape of dots, the model that we need to use might need to be any of the three types of models that we've used this year, right? So linear, we've talked about linear graphs, linear models, where a straight line would represent those data points the best. Quadratic models, where maybe a parabola, a U, would fit the shape of those points the best. And we also talked about exponential functions, a little bit of a learning curve, and we'll have to remind ourselves of what that looks like in a minute too. Sometimes data points fit into an exponential function as well, or an exponential model. So we need to be able to tell the difference. Okay? So that's what our point is today, to be able to classify a linear, quadratic, or exponential function. And we want to be able to tell if we have a graph, which is going to be the easiest, an equation, which should be the second easiest, and then a table is going to take some work, but we can fight through it. Linear. Remember what a linear model is. Linear, the word line is in linear, so these are our line graphs. These are our line equations, right? So normally we write them in slope-intercept form. Y equals mx plus b is our linear model. And we know that when we graph a linear model, it looks like a line. So something like that. So some examples of linear models. Y equals negative 3x. Y equals 1/2 x minus 11. Or y equals 8 is a linear model too. Y equals 8 is a horizontal line, but it's still a line. Okay? Quadratic models. Remember that quadratic is what we've been working a lot with here lately. Your standard form for a quadratic model is not slope-intercept. It's this, right? Y equals ax squared plus bx plus c. Hopefully we know that the graph of a quadratic is called a parabola and looks like that. And some examples of quadratic functions might be y equals negative 3x squared, y equals 1/2 x squared minus 11x plus 9, or y equals x squared plus 9. Okay, anything like that. And then exponential. You have to remember exponential functions look something like this, right? Where your x variable is an exponent. Why it's called an exponential form. X is an exponent. So it takes on a form like this. Y equals a times 1 plus or minus r. And that's not, plus or minus not always in there. It's not like quadratic formula where it's always 1 plus or minus, right? And we'll see some examples in a minute. But the graph always looks something like this. It was a what we call there's a learning curve, right? But it starts out sort of horizontal and then really sort of curves itself up to almost vertical. Okay? So an L, maybe, backwards L. Some examples. Negative 3 to the x is an exponential, or 1/4 to the x is an exponential. Or y equals 6 to the x is an exponential. Okay? So there's not a plus or minus in there every time. As a matter of fact, you're going to know what a is and you're going to know what r is, just like you know what a, b, and c is in a quadratic model, and you know what m and b are in a linear model. But you're not going to see that plus or minus. Okay? So those are all exponential models because x is the exponent in the function. All right? Now, from a graph, which of these is linear, which is quadratic, or exponential? Oh, sorry, not from a graph first. We're going to do it from the equation first, from the function first. Okay? Y equals 5 to the x. Well, since x is an exponent, this is exponential form. Okay? Next one, y equals negative 2x squared plus 8. Right? That squared tells you that this is a quadratic. Okay, anytime you have a variable that's being raised to the second power, it's a quadratic. Last but not least there, then this guy must be your linear model. So I'll write them back up here again. This is your quadratic, and this is your exponential, and this is how we're going to tell. If x is an exponent, it's exponential. If your variable is being squared, it's quadratic. And if you have an x to the first power, that's it, it's a linear. Okay? All right. Now by graphs, right? What kind of model are we going to use here? Well, it's a straight line, so hopefully you're saying linear, right? What about this guy? Well, it starts out horizontal, and then really jumps up to vertical. So this is your example of an exponential model. Would be appropriate. Here we got that u. Use a quadratic, right? So this is linear. This is exponential. And then this guy down here is quadratic. All right? Now, from a table, there's a way to tell if you just have a table of values. If you have a t-chart, no graph, no exponential function, you just have x and y coordinates that are mapped out together. Okay? And I'm going to change one of these. But if it's a linear function, then the difference between the x's and the differences between the y's are going to be consistent, right? They're going to be the same. So the difference from one x coordinate to the next x coordinate in our 2 points will be the same all the way throughout the table. And the difference between the y coordinates are going to be the same all throughout the table. Okay? In the quadratic, it says that the second difference is the same. And that doesn't make a lot of sense to me. So what I'm going to say is that the differences are symmetrical. Okay? Parabolas are symmetrical, right? You can cut them in half and you get the same thing on both sides. So as long as the differences in the y coordinates are symmetrical, then you're looking at a quadratic. And I'll show you what I'm talking about. And then exponential, if the differences are not the same, if the differences in the y coordinate are not the same, across, down the whole table, whether they're not symmetrical and they're not the exact same, then what we'd want to do is we want to check out the ratio. We'd want to divide the second y coordinate by the first and go all the way down the table doing that and seeing if that division is the same. See if that ratio is the same. And if it is, then it's exponential. Okay? So, for example, we have this table here. Now, the best way to do this is to line up your coordinates so that the difference between the x coordinates is the same all throughout. So for every table that you see, we have come up with values, we've come up with y values for -2, -1, 0, 1, and 2. For every table, whether it's linear, quadratic, or exponential, they're all going to be -2 to 2. Okay? So what we really want to focus on is the y column. What's going on? Is there a difference? Is there a consistent difference? Is there a symmetrical difference? If not, then we got to look at ratios and start dividing some stuff. Well, the difference from -4 to -3.5 is a half. The difference from -3.5 to 3 is a half. And the difference from -3 to -2.5 is a half. And from -2.5 to -2 is a half. So since this difference is the same all throughout, we're looking at a linear model. We don't have to worry about dividing anything because we have a consistent difference. Okay? Same here looking at this. Right? Our x coordinates go down from -2, -1, 0, 1, and 2. And then look at the y column. The difference from 10 to 7 is 3. From 7 to 4 is 3. From 4 to 1 is 3. And from 1 to -2 is 3. So it's a consistent difference all throughout your y coordinates. This is going to be a linear model again. If we were to plot those points, we would get a linear graph. We could graph a straight line. Okay? Look at this one. X coordinates, again, are in order from -2 to 2. Look at the difference from 4 to 1 is 3. The difference from 1 to 0 is 1. Well, shoot, we don't have a consistent difference. Now, is it symmetrical? Well, the difference from 0 to 1 is 1, and from 1 to 4 is 3. So is it symmetrical? The answer to that is yes. It's symmetrical. Since a parabola is symmetrical, that means that this is going to be quadratic. If we were to plot those points, we would be able to graph a U. Okay? Same here. All your x's are lined up. Difference from here to here is 9. From here to here is 3. 3, and then 9 again. And so since it's symmetrical, we're going to be able to use a quadratic. Okay? Now, an example of an exponential. All of our x's are lined up, and these are our y coordinates that happen to go with these x's for this particular model. Well, if we were to subtract here, we'd get 0.4445, right? The difference from here to here, well, 2 minus 0.6667 is going to be 1.3333, so not the same. And if you look for symmetry to see if the differences are symmetrical, 6 minus 2 is 4. We're not going to get it. So these differences are not going to be the same, and they're not symmetrical. So what we need to do now is divide, look to see if the ratios are the same. In other words, divide 0.6667 by 0.2222. And when you do that, you're going to get about 3. Pretty close. And it's not going to be exactly 3 because we're kind of rounding. Now, if you divide 2 by 0.6667, you will get pretty close to 3 again. Obviously, 6 divided by 2 is 3. And obviously, 18 divided by 6 is 3. So this ratio is constant. The ratio is the same for all of our y coordinates. So that makes this guy an exponential. So the moral of that story is if the differences aren't the same, if they're not consistent all the way down, or if they're not symmetrical differences, then go start dividing the second y by the first y and see if all of those are in the same ratio. So this would be the same ratio. It should be 3 to 1, but I'm just trying to make this easier on you. So since they're all, divide them all out and you get 3, this is going to be an exponential. Okay? You would discover the same here, I believe. X's are lined up. You can try the differences. The difference here is 36. The difference here is 9. The difference here is like 2.25. So it's not going to be symmetrical, and it's not the same difference all the way through. So we start dividing. 48 divided by 12 is 4. 12 divided by 3 is 4. 3 divided by 0.75, if you type it into your calculator, will be 4. 0.75 divided by 0.1875 will be 4. So it's the same ratio, so this is going to be exponential. If you were to graph those points, you would get an exponential graph. Okay? That's all there is to it. So try this out. Your homework is out in Canvas. Get started on it. And make sure you have that done by next time.